Okay, in the previous lecture, we saw the animation of the car boot mechanism. We came pretty close to the actual dimensions. Now we are going to look at here in this particular case, we started off with assuming where the fixed pivots were going to be. Um, so we did the design based on that. So we did the design based on that. Now, instead one can choose the floating pivot locations. This will be on the coupler. As I said, this will not be always practical as the design fixed pivot locations may not fit on the frame. But anyway, we will do this design also. So now let's say I have these three positions. This is not a car body, but this is simply three different positions: A1, B1, A2, B2, and A3, B3 of a line on the coupler. And now what I have done is earlier I was very particular. I said those A's and B's were not the fixed pivots. I mean, sorry, the floating pivot locations, but simply GeoGebra drawing points to show the end of the line. But here A1, B1, A2, B2, and A3, B3 are the fixed pivot locations. So therefore, I have decided that the endpoints of these are where I'm going to locate the fixed pivot. All right. The design philosophy is basically the same. We go to an inversion. We say like imagine that through these three positions. So I join A1 to A2. Similarly, I join A2 to A3, and I do the same for B1 to B2, B2 to B3. So the construction is very simple. So we do this, and then what we do then is to draw perpendicular bisectors. The perpendicular bisectors basically from A1, A2, A2, A3 perpendicular bisector gives me O2, which is at the same distance from A1, A2, and A3. And similarly, the perpendicular bisectors of B1, B2, and B2, B3 gives me O4, which again means that they are at the same distance from the point P. So when we do this, I get a design. I've just done some of these things. It's L1 equal to 7.2 millimeters, very small. You can see that here in the thing, which is a very small. In fact, S becomes so in effect, S becomes the fixed link. L2 is 22, L3 is 25, and L4 is 37. This is a Grashof mechanism. You can see that L4 is the largest, which is 37, plus 7.2, which is 44.2. If I add these two, I get 47. So therefore, it is a Grashof mechanism. But this is a double crank Grashof mechanism that I come up with. Okay, so here is the animation which will show you that it is going through these three positions. Let us open that up and make this, let me see. It's opened up. So you can now see it's a double crank, and EC is the coupler. You can see it occupies this position A1, B1 first, and then occupies the position A2, B2, and then the position A3, B3. So you can see, I'll play it again. You can visualize it is passing through those three positions. That the uh, 4-bar mechanism that we have designed, basically you can see now it coincides with A1, B1, coincides with A2, B2, and now coincides with A3, B3. So this is a double crank that we have designed, which will basically go through those three configurations. All right. Now, the last topic that we are going to go. So, therefore, so we have now done a motion generation, two cases. One where we fix the fixed pivots. In the second case here, we have seen we have chosen the floating pivots and then come up with where the fixed pivot location should be. All right. Now, the last topic, which I'm not going to deal with in a very wide fashion, like what typically happens in books. There's a very detailed coupler atlas that is produced, different kind of curves and so on. I'm going to show this in a more intuitive, animation oriented way. And those interested can go and do this, can try to mimic this animation and then look for themselves what kind of coupler curves they get. Uh, as in a 4-bar, the coupler happens to be the most interesting link, obviously, because the motion is more complex than as it is a combination of rotation and translation. And if I pick a point on the coupler, the motion is basically a high degree polynomial. Degree here is the highest power representing the curve which is traced by the coupler. Interestingly, for a slider crank, the connecting rod basically is a fourth order, and when you go to a 4R mechanism, which is all revolute joints, you get a sixth order curve. That is the order of the curve. Now, all linkages with one or more floating coupler links can generate such curves. As we include more links, more complex coupler curves can be generated. We are not going to look at anything beyond a 4 bar. Someone called Wunderlich basically came up with an equation which says that the degree of the curve that you can get is 2 times 3 to the power of n by 2 minus 1. In our case, n is 4 links. That is what we are going to deal with. So therefore, we have 2 into 3, which is a sixth order. But if I go to essentially a 6 bar, you can see that I can get an 18th degree curve. So obviously, a lot of different paths can be represented by that 18 degrees. All right. So the coupler curves basically are very useful in terms of path generation devices. You can use it to approximate straight lines. We tried this before. I guess you guys can do this somewhat better than what I have done. We can also use this to basically do large circular arcs when we do what I call as cams. I will show you some of these things. They come in a variety of shapes. So this shapes is what makes the coupler atlas. And but I am just going to show you a video, and I am going to move around this coupler point that I have in the video, and you can see the various shapes that are coming. And I will just comment on the various types of things as we see the video. Hopefully I will freeze it at various locations and then explain what kind of things we will get. All right. This I have done using GeoGebra, and you can see that this is a template that I have constructed. I can pull the various points here, and this would accordingly change in shape, but I'm not going to do that in this. So you can see that already one of the locus for the snapshot that I have taken, this looks like what? Banana. So banana type is one of the coupler curves that you are going to get. So let's go through this. Let me open this up. Let me make it full screen here. So you can see that banana now becomes a very sharp curve. In fact, you can see a kind of a cusp. So we will freeze here. So you can see I'm basically now when I look at this, I have a very sharp thing which is a cusp. But this is basically a point of zero velocity. So it's like a instantaneous center. If you want to compare this, this is a very sharp cusp. Let me roll it further. So you can see it becomes fatter and bigger, kind of ellipsoidal. Now let me freeze. Again, we are going to head towards a cusp. But one of the things that you can see is in this portion of the coupler curve is basically a straight line. So, I could randomly do this and then come up and say, look, if I were to use this portion for my path generation, this would be. So you can see here that it is more of a straight line than what I came up with, and you can also see this is somewhat circular, so I can use three precisions to go through a circle like this, and I can use this to go through a straight line like this. So this is one type of coupler curve that you can get. So you can see a sharp cusp, and now here you can see a kind of a twist. So the curve basically now kind of goes through what was a single curve. Now I have a fold in this, or basically like a Lissajous curve. So you can see that I can get such complicated curves using the coupler. So it becomes bigger, and now we are heading back as we go along this cusp, and then now it's a big fat ellipse. So again, you can see here in this particular locus that it is almost a straight line, and over here some parts of it are almost a circular path. So this is heading towards an ellipse as we go along. The ellipse is becoming like a kidney bean shape as we roll this coupler point, and I have just pulled it further, and you can see back again these kind of curves that come. So this is another case where I have I can have a straight line like this or a straight line like that. Over here you can see that that part of it is straight, so you can see that the complexity of the coupler curves is visible in this kind of a video. So yeah, now again it folds, and again I'm coming back just to show you the transition, and then again, yeah. So you can get all these kind of shapes. Okay, good. So let me just play again. I will not say anything. You can just visualize the various shapes that it goes through. Okay, so this with this we will basically close the as I said, the coupler is a very interesting mechanism. With that, we will close. This video was the last one that I had. So, as I said, I'm not going to get too much into this coupler curve design. As I said, most of it is graphical, and you can always go refer to textbook, either Professor Malik's book or Norton's book to get more ideas about this. With this, we will basically wrap up the first part, the kinematic synthesis part of it. So, to summarize, what have we seen? We have seen how to use a 4-bar, basically a crank rocker design, given a certain crank rocker rocking angle between the two extremes, and alpha, which dictated a time ratio. We had a positive alpha and a negative alpha. I've explained that negative alpha. Some of you had asked nice questions, and I think the text will undergo some transformation to reflect the replies that I have made. Um, we also did special cases where theta equal to alpha, theta by 2 equal to alpha, and so on. So these things were done, and then we said to check the design, we need to look at the transmission angle, and we want to ensure that it is between plus or minus 90 plus or minus 50 degrees. And if the design doesn't satisfy that, we'll have to go back to the drawing board and come up with another design. Then we have looked at path generation. In path generation, we did plain path generation with 3 precision points, fixed pivots. Then we also did with timing, which means that we basically specified how much crank angle should be there between the various positions. And after this, we did motion generation or rigid body guidance, where we did one a car boot lid example where the fixed pivots were chosen, and then we located the the coupler floating pivots based on 3 orientations, positions of a line on the coupler. And the last one that we did in motion generation was basically one where we allowed we kind of chose the floating pivots on the coupler, and then from there worked backwards and got the fixed pivots, and I showed you an animation that it passes through those 3 things. And then we very briefly discussed coupler curves, mostly through an animated video showing you the different kind of coupler curves that can come as which we can use for different aspects of path generation. All right. Okay. So then the next week onwards, we would basically switch gears, rather not switch gears. We will go to CAMS, which is a very important higher order mechanism, higher order, which has higher pair mechanism. So we have higher pairs in them. This will be the first instance that you will run into something like this, and later Dr. Abhijit will talk about gears, which also form another higher pair mechanism, a mechanism which has higher pairs. Okay, so let me stop here, and we will check back next week with CAMS.